Welcome back, everyone. This is our screencast about solenoids and um, electromagnetic induction. Okay, so we saw earlier that a moving electric charge acts like a magnet. So when current goes through a wire, the wire itself produces its own magnetic field. So we can use this to basically create an electromagnet. This is a really useful thing. Okay, so a solenoid or solenoid, I use kind of both terms interchangeably, is just basically a coil of wire. So we have here a coil of wire, and what that shape of wire does is it allows the creation of a strong magnetic field in there, and that essentially acts like a bar magnet. Right there. So I'm going to show you a short video. There's nothing to this really. This is just a representation of the magnetic field as the solenoid is as current starts to pass through it. So we'll just play that really quickly. So that's as you add that up, and one of the things I want you to notice is that you can see by the density of the lines, the magnetic field is very strong inside, and outside it's much weaker. And essentially, we just assume that it's essentially zero outside here. So if you look at these magnetic field lines, though, it looks like the magnetic field due to a bar magnet. And so the question, of course, is going to be how strong is that magnetic field? What does it depend on? And how do we tell which direction it points? But again, this is a big idea. So the idea that we can have magnets that we can turn on and off is a really useful thing. So you may have seen video of a scrap yard, and they have these gigantic electromagnets that move scrap metal around, and then you can turn the magnet off and it dumps it somewhere. There are all sorts of uses for this. Okay, so first of all, the question of which way the magnetic field points. Okay, so the magnetic field, if you think about it, is going to depend on a few things. It's going to depend on how much current is running through the coil of wire. It's going to depend on how closely spaced the coils are, and the strength of the field, or the direction of the field, is going to be determined by which direction the current is going. So in this coil of wire, you have to pay attention to the way they draw it. So we have another right-hand rule. So this is our second or third right-hand rule here. So when it comes to the right-hand rule, in this one, your fingers curl around in the direction of the current. Okay, and your thumb points in the direction of the magnetic field. And usually we are actually concerned with what direction is the magnetic field inside the solenoid. Okay. So you can see here without the hand, so in this case the current is going up, and you see the way it's drawn, and it's going up. So in the front of the coil, the way we're looking at it, the current is going up and over the top and then around behind. So that's the same way that they have it drawn here. So the fingers point up and then curl around over the top. If you change the direction of the current, then the current would be going behind, and it would be going up behind the coil and over the top that way. So that would change that. So that's the way you use that right-hand rule. Okay. Now for the formula for the magnetic field, I've made a strategic choice here to not go into all the details. So there's something called Ampere's law. I'm trying to decide if I want to bother with that or not. This is one of those cases where it's not going to be on the AP test. It's not extremely useful, and so I may come back and talk about Ampere's law in some detail, but for right now, well, I'm not going to worry about this. And like I said, I may come back and do this Ampere's law thing. To make a long story short, the magnetic field inside a solenoid is equal to mu naught. So that's our permeability constant, times I, which is the current, of course, and N. And N is the number of turns per unit length. I'll write that down here. So B is equal to the magnetic field, and remember we always measure that in Tesla. Okay, we have mu naught, which is the permeability constant, which is 4 pi times 10 to the negative 7th. I is equal to current, and that is going to be in amps. And N is equal to the turns per unit length. So turns is just a counting number. There's no units on that, and length is obviously going to be meters. So the units on that are going to be 1 over meters. So when it comes to turns per unit length, they may say something like a solenoid is 15 centimeters long with 100 turns, or 100 coils. Coils and turns are basically the same thing. Okay. So when we're figuring out the turns per unit length, it's really simple. N there would equal 100 over 15. And that would be in centimeters, and you probably want to change that to meters. Let's just go ahead and put that as 0.15 because we want to, so that's turns 0.15 meters. And you can do the math if you want. That's really not the important thing. So this is an easy formula to use. It's really straightforward. It's given on the AP formula sheet if you needed it there. So it's just there. No, you can look it up either in your notes or in your book. It's easy to find. So solenoids are pretty straightforward. Like I said, it's the derivation of this that's actually the complicated part. But I'm going to go ahead and move on. So at this point, what we've looked at is we know that we can use electric current to make a magnet. So the next question is, can we do the other way around? Can we use a magnet to make electric current? Because if we can do that, then that is a real game changer. So I'm going to show you. The short answer is yes, because that's basically responsible for our entire way of life here, is being able to produce electricity here. So we know that. So I'm going to show you another video. It's about 5 minutes long. That is going to be an introduction to this and what we want to pay attention to are the conditions needed to make this happen. So actually, I'm going to pause the video so I can set the sound up. Okay, so we're back.
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have this single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. If I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also. We saw that as the number of turns in the coil increased, the current increased. So the current is proportional to the number of turns, which we'll use N to represent.
Okay, so I'll go over the mathematical details here in a second. So the big idea here is that how do we make electricity with a magnet and a coil? It seems like we have to have a moving magnet. You could also move the coil. So in the induction process, so a current, although technically we measured current because we had a conductor there, technically an EMF is induced in the loop by a changing magnetic field. So you saw in the video, if the magnet it can be inside the coil, but if it's not moving, then the magnetic field's not changing and there was no current. So we got the current when the magnet was moving, and you could see the more quickly the magnet was moving, the greater the current we got, because the rate of change of the magnetic field was greater. So this is the basis behind all electric generators. That's what they do. You have magnets, you have coils, and you have a changing magnetic field within that. So there are different ways of constructing it, but it's all the same thing. So this was discovered in the late 1800s, and it's at a time where steam was used to basically as the power source for trains and factories and things like that. Now we have a way of producing electricity. And a generator and a motor are very similar to each other, so it didn't take long to figure out how to make motors and generators once this idea was discovered. Okay, so just a little bit of detail. We need the concept of magnetic flux. Okay, we talked about electric flux when we talked about Gauss's law. So it's the same thing. So with our definition of electric flux, we still use phi. Okay, put a little b for magnetic because this is the magnetic flux. The definition is b dot dA, the integral of b dot dA. Okay. But in our case, again, everything that we do I can only think of like one or two random problems where the magnetic field is not perpendicular to the surface there. So if we have a uniform magnetic field, okay, so it is constant strength throughout all the area, and or that is perpendicular to the surface, then the flux, the magnetic flux, just turns into B times A. Okay, and that is what we use 99.9% of the time. So that's the magnetic flux. Okay. Now this is used in a different way than Gauss's law, for the simple reason that Gauss's law, we had a Gaussian surface and all that kind of stuff. We were trying to calculate values for an electric field. This is used with Faraday's law of induction. So Faraday's law of induction said that we can induce an EMF, okay, and that is equal to the rate of change of the magnetic flux inside a coil of wire. Okay, so if we put this in the form of a formula, so we have the EMF, okay, we've got a minus sign up front, and the minus really doesn't mean anything. It's just which direction the flow is going to go, but we're not going to get that from the sign. We'll have yet another right-hand rule to figure that out. Okay, so the minus sign is really not important. Very often they just ask about the magnitude of the electric or the induced EMF. So rate of change, oh, rate of change, that's a derivative. You're good calculus students. You should immediately think derivative when you do that. So the rate of change of the electric or the magnetic flux is going to be d phi dt. So that's the big idea. Now, in the video, we also saw that basically this applies to every coil or every turn in the coil. And so if you have 10 turns, you're going to get 10 times as much EMF. And so we actually have to add on to that. So this is for basically a single loop. And so if we have multiple loops, we just multiply by n. So the induced EMF is equal to minus n d phi dt. So that is the big idea behind electromagnetic induction. And I think today I just want to stop there. Let me see what the next slide is. I forget what that is. Okay. Actually, so let's do this one problem real quick, because it combines the solenoid and the induction formula. Okay, so we have our solenoid has 220 turns per centimeter and carries 1.5 amps of current, and they give us a diameter, so we can figure this out. So and okay, so we have this. So what I've got, let's start off with the solenoid. So if I can draw this, we've got that coil. That is really horrible. Okay, so inside there, so we've got N is equal to 220 turns per centimeter, which would equal 2,200 turns per meter. And we've got a current running through that of 1.5 amps. Okay. And they tell us when this is turned on, okay, actually it's going to be reduced, so basically we're turning it off. Okay, so what we really want to know, to find out the induced EMF, we need to find the change in the magnetic field. So the change in the magnetic field is, it's going to go down to 0. So we need to know how much it starts at. So the magnetic field of the solenoid is mu naught times I times N. So we're going to have 4 pi times 10 to the negative 7th times I, which is 1.5, times 2,200. Alright, and let me find my calculator here. Okay, so we're going to have 4 times 3.14 times 1.5 times 2200. So we're going to have, so B is going to equal 41,000, basically 450, times 10 to the negative 7th, or 4.145 times 10 to the negative 3rd, and that would be Tesla. If you want to, you call that 4.145 times, or millitesla. Let's just keep it in Tesla. Okay. And so now we know that the induced EMF in this coil, okay, we need to find the magnetic flux. So we have to be careful. So this is producing a magnetic field inside here. So we've got this magnetic field that starts off with this value and ends up going down to 0. I'm just choosing a direction for no good reason. Okay. And now we're going to place a coil with 130 turns in it. So the idea here is that inside this solenoid now there's this other coil of wire, okay, and we're going to hook that up basically to a meter and see what kind of EMF we're going to get. Okay. Okay, so the induced EMF, again they said magnitude, so the negative sign is not going to matter. So we're going to have N d phi b dt. So N is going to be 130. Okay. Now when we talk about d phi b, okay, so phi is going to be basically, so we're talking d dt of our magnetic field times the area. So again, we're arranging this so we don't have to worry about angles and all that. So the magnetic field here is going to be perpendicular to the loop. Okay. Now B is going to be changing, A is not. Okay. So we can bring A out front, it's a constant, so we're going to have 130 times A times dB dt. And now this is a case where we need to ask ourselves, do we really need to do calculus here? So the magnetic field is changing, but we can assume that it's changing uniformly over this 25 milliseconds. Okay, so in other words, the b is not really a function of time in that sense, so we can do deltas. So we're going to have 130 times a times the change in b over the change in time. Okay. So we're going to have 130. The area is going to be pi r squared, so we're going to have pi. The radius, we'll use the 3.2 centimeters, so it would be 0.032 meters squared. And then we're going to have 4.145 times 10 to the negative third over the time of 25. Since that's milliseconds, 25 times 10 to the negative third. So if I write it like that, I can cancel those out. Just makes my life a little easier. Alright, so let's go back to the handy calculator. And so we've got 130 times 3.14 times 0.032 times 0.032 times 4.145, and we're going to divide that by 25. Okay, so our induced EMF is going to be 0.069, and it's an EMF, so that's going to be in volts. So this is actually more complex than a lot of the problems we're going to do. But I just wanted to give you a sense of how we could use those two together. Now, in terms of homework, I'm not going to do book problems for this chapter. This is one of those chapters where I just don't like any of the problems that they have. So there will be a quest assignment, and I'll get that posted sometime in the near future. But for now, this is good for today. And your next assignment will go into a little bit of Lenz's law, which is very interesting, and then some more problems. So that's all for today.